In summary, here's how open loop position control for DC motors works. Step 1 is to decide on either a speed or a time duration for the move. Step 2 is to calculate the voltage necessary to achieve the speed that you set in Step 1. If in Step 1 you decided on a time duration for the move, simply divide the distance of the move by the time to get the speed. The equation that you use for Step 2 is like this. The voltage that you need to apply to the motor divided by the maximum voltage that the motor can take, or the rated voltage of the motor, is equal to the speed that you desire divided by the maximum speed, or the rated speed, of the motor. In the example shown in the last video, we were using a motor where we knew that the maximum voltage was 9 volts. And we knew that at 9 volts, the speed that was achieved was 100 millimeters per half a second. You can figure out Vmax and Smax either from a data sheet from the motor, or you can simply test the motor. If you apply a known voltage and can measure the speed that the motor produces at that voltage, you can find these two numbers experimentally. Now, after you've calculated the voltage necessary to achieve your desired speed, the V applied for the S desired, you can move on to Step 3. Step 3 is to calculate the duty cycle that achieves the applied voltage that you calculated from Step 2. We talked about duty cycle in the last class period of videos, but I'll give you a reminder here as to how you calculate the duty cycle. The duty cycle can be very simply calculated from the equations in Step 2. The applied voltage divided by the maximum voltage is equal to the duty cycle and since the duty cycle is typically expressed as a percent, you have to divide the duty cycle by 100. Now, if you happen to not know the V applied and the V max, note that V applied over V max is also equal to the speed desired over the speed max. So you can also calculate the duty cycle from the speed. Now, once you know the duty cycle that you have to set for your pulse width modulated signal, there's one last step that you have to do. Step number 4 is to calculate the time duration for the move. You get the time duration for the move from the desired speed and the desired position, or the desired displacement, of the move. So you can calculate the time duration like this. The time duration for the move is equal to the move distance, which for us we are representing as d, the displacement of a prismatic joint, divided by the desired speed. Once you've calculated both the duty cycle from Step 3 and the time duration from Step 4, you can now achieve this move on your joint with your microcontroller by Setting the pulse width modulation signal of your digital output pin to duty cycle for amount of time. We'll practice doing this in class. Now, this 4-step process for doing open loop position control for DC motors has some pros and cons. The pros are that this approach is very simple and it requires no additional sensors. In fact, requiring no sensors is the definition of open loop control. When we get to feedback control, we will see that we always need to have sensors for feedback control. So one of the pros of open loop control is that it's very simple and it requires no sensors. But open loop control also has some cons. One is that it's not very accurate. The accuracy of your joint positioning with open loop control depends upon both the accuracy of your timing and the accuracy of your knowledge of the motor velocity constant. The motor velocity constant is affected by things like the load at the end of the end effector and friction internally to the motor. And so we'll find that when we use open loop position control, the end effector does not always end up getting to the position we were intending it to get to. Another major con of open loop position control is that it is sensitive to disturbance. That means that external forces like the wind blowing or something in the environment bumping into your robot, things like that, can dramatically affect the accuracy of your positioning. When we try this in class, you will see that you are able to easily affect the positioning of the slider in your prismatic joint by simply taking your finger and bumping the slider. And when you do that, you affect the positioning, and the controller is not able, with open loop position control, to correct for the fact that your finger has come in and bumped the slider and moved it out of position. A related drawback to open loop position control is something called drift, which means that the positioning error can increase over time. This drawback is very similar to the sensitive to disturbance drawback to open loop position control. If an external disturbance, like your finger bumping the slider, comes and moves the slider out of position, the controller is not able to compensate for that. And so the next time something else comes and bumps the slider, the error will increase, and over time the slider will become more and more out of position, and you will need to periodically re-zero the slider in order to get it back into position. So these are some of the major cons that we have with open loop position control, and we'll be seeing in future videos how we can improve our position control to compensate for these drawbacks by introducing feedback.